So this is the last that I'm going to, or the last that we need to really kind of explore with respect to fatty acid synthesis, and this has to do with the elongation of fatty acid chains that are 16 carbons or longer. First of all, they are done, or that is done, elongation beyond 16 carbons, so if you're synthesizing like a 20 or 22 carbon long fatty acid, that's going to be done on the endoplasmic reticulum and in the mitochondria. It follows a very similar pathway, but one thing that I'd like you to notice is we've got an acyl-CoA and an acetyl-CoA. One fundamental difference between that is shown down here in that we are not using an acyl carrier protein. So when you're elongating with these different fatty acid, or these different carbon contributors, you're using that coenzyme A variation of it. So your substrate is acyl-CoA rather than your acyl ACP. That fatty acid elongation in the mitochondria is unique because it uses that. Likewise, it uses acetyl-CoA rather than malonyl-CoA, which is what we're using whenever we're synthesizing fatty acids, which that is up until 16 carbons that's going to take place in the cytosolic space. But other than that, most of what you're dealing with is very similar reactions. Now, I'd like to bring you back to this slide right here, and this that I've just drawn a little star by, which as you guys can see through all these videos that I'm really not getting any better at drawing any asterisks or anything like that. One thing that I'd like you to recognize is that malonyl-CoA, well, that inhibits the transfer of fatty acyl-CoAs into the mitochondria. That's something worth noting because that's basically like saying if malonyl-CoA is present, then what we're trying to do is we're trying to do fatty acid synthesis. And so in the event that malonyl-CoA is present, well, then we probably don't want to be going through beta oxidation. Even though this pathway is completely separate, it is in the mitochondria rather than the cytosolic space. We still want to be, well, synthesizing fatty acids rather than seeing them ultimately go to be broken down by having them get transported from a fatty acid, or I'm sorry, get converted from a fatty acid to fatty acid CoA, and then ultimately transported into the mitochondria. So that's one mechanism by which these two reciprocal pathways are kind of controlling one another. Now, this is kind of where we get into a little bit of a, I don't know, kind of a potpourri component of this of this material. Animal cells are going to have fatty acids that are delta 4, delta 5, delta 6, and delta 9 fatty acid desaturases. So you can make those double bonds present. You can add those double bonds. And one thing that's worth noting, if you think back to like buying Oreos or eating McDonald's foods, you always see the label that says no trans fats are present. Well, all natural double bonds are going to be in the cis position. And so if we have fatty acid desaturases that produce those double bonds, well then there are some fatty acids that we have, for instance, linolenic acid. That's an omega-3 fatty acid. That's something that we can't synthesize, which is why if you listen to a nutritionist or a dietitian or something like that, they'll say, oh, well, you need to eat salmon because they're rich in omega-3 fatty acids because that will prevent or inhibit inflammation or something like that. So that's because you have to supplement for these anytime that you're consuming something or ingesting something that has a double bond beyond that 9 position. So these two, linoleic and linolenic acid, are both fatty acids that you cannot synthesize in your own body or in any of your cells. So these fatty acids ultimately are going to be precursors for eicosanoids, which eicosanoids are 20 carbon fatty acids, and they're helpful in waterproofing skin as well as in the production of prostaglandins, leukotrienes. They're involved in pain regulation, fever, and blood clotting. Now, here we see some actual examples. So here is arachidonic acid. Arachidonic acid is a 20 carbon long fatty acid with a total of 4 double bonds. So arachidonic acid and eicosanoid, which I believe eicosanoid is derived from Greek because eikos, I think, means 20. Not to make that mistaken with the yogurt, which I think is oikos. I'm not sure. But eicosanoids are 20 carbon long fatty acids. Arachidonic acid is an example of one of those. Now, there's an enzyme known as cyclooxygenase, or a class of enzymes known as cyclooxygenases, that what they are going to do is they're going to take this arachidonic acid and they're going to make that ring there. Okay, they're going to cyclize part of that fatty acid. Now, the significance of that is after this structure right here has been formed, well then a peroxidase is going to come along and basically make something that will lead to production of prostaglandins, as well as something that will lead to produce thromboxanes, which will lead to blood clotting. Now, when you think about this, it's these molecules, so prostaglandins, other prostaglandins, that will lead to the development of a fever or any sort of pain. Now, aspirin is an example of a drug that blocks this enzyme, cyclooxygenase, or this class of enzymes, cyclooxygenases. And so whenever you think about taking aspirin to relieve pain or relieve a fever or lower a fever or something like that, essentially what it's doing is it's blocking the production of this cyclized arachidonic acid and ultimately preventing the production of these prostaglandins. So what aspirin's doing is it's acting as an inhibitor to cyclooxygenases. Now, there are two very well characterized cyclooxygenases. There's COX-1 and COX-2 enzymes. There was, I cannot remember exactly what the name was, but there was a drug on the market for a time that was believed to be, or it was identified as a putative inhibitor of an enzyme, COX-3, and so it was believed that there was this third cyclooxygenase enzyme that was unique and different from COX-1 and COX-2, but effectively did a similar thing. So it was this idea that, oh, well, we've developed this drug that inhibits this enzyme that basically Tylenol is not able to inhibit, and as it turns out, that was kind of inaccurate. I believe that I can't remember what the drug was, but the conclusion was there was not actually a COX-3 enzyme. Instead, this enzyme was, or this molecule, this drug was working as an inhibitor simultaneously of COX-1 and COX-2. So the point is, with these enzymes, whenever you inhibit them, well then you're going to reduce blood clotting, you're going to reduce pain, you're going to reduce inflammation, and that's all good and well. Aspirin is very effective for doing those things, but it can cause stomach bleeding, kidney failure, and sometimes it can even be fatal. At any rate, this is kind of a potpourri section of fatty acid synthesis. I hope this is helpful, and thank you all very much. Have a good one.